series on machine learning based prediction of malaria. My name is Dennis Mureithi, a statistician by training and an associate professor of applied statistics at Chuka University, Kenya. Once again, let me take this opportunity to welcome all of you to this webinar training, and thank you for finding time to be with us. The theme for today's training is optimal machine learning models for malaria prediction. It's important to note that this webinar will last for about 2 hours, and the webinar is being recorded. The recording will be made available via the WhatsApp group. This training is delivered by machine learning group leader, Professor Olawale. And for those who are joining us for the first time, I think it will be important if I introduce Professor. So let me give you a small biography of Professor Awe. Olawale Awe is a distinguished Nigerian statistician, professor, and data scientist. He is currently the team lead at the Statistical Learning Laboratory of Federal University of Bahia, Brazil, and President ADA Global Academy. Professor Awe is actively involved in research and outreach initiatives that promote the advancement of data science and its practical application worldwide. Professor has published over 100 scholarly articles in reputable journals on machine learning and other interdisciplinary areas. This month, MIFA Open University appointed Professor Awe as Distinguished Professor of Data Science. So members, as we learn from Professor, also get time and congratulate Professor for this achievement. I'm happy to invite Professor to guide us on the next step. Welcome, Prof.
Thank you very much, Professor Dennis. And I want to welcome everyone to this month's webinar. We are grateful unto God for sparing us to see another month end. Every end of the month, we usually have this webinar. And we are glad to be here again. So as usual, we're going to have this talk for 1 hour or thereabout, and then afterwards, we will take questions. I'm going to start with my slides, then I'm going to go into the practice. I'm going to demonstrate practically. And so let's pay attention. Please note your questions down. If you have questions, please note them. I'm going to take all your questions at the end. So today we are considering understanding hyperparameters, the key to optimizing machine learning models. Last month, we saw how to build models in Caret. And we also considered how to balance the data before applying the data to the models. Now, today, I'm going to give you a consolidated approach on how to do all this in a wrapper. And I'm going to go slowly so that you can really understand. But before then, I want to say something about hyperparameters, setting up your hyperparameters. Now, what are hyperparameters? What do you mean by hyperparameter? Hyperparameter is a configuration or setting in the machine learning algorithm that is usually set before the actual learning process of building, model building process begins. And it is external. It cannot be learned from the data itself, or it is external. It doesn't have to do with the original data. So they confirm the overall behavior of the model and can influence how the model learns and performs. So unlike usual parameters that which we learn from the training data, such as weights in neural network, hyperparameters, usually external configurations that you must define before training your model. Now, hyperparameters are very useful because they allow data scientists to tweak model performance for optimal results. If you're not satisfied with your model results, you resort to hyperparameter tuning. Sometimes it could be optional, but sometimes it could be necessary because really essential in machine learning and in choosing the appropriate model. Hyperparameter tuning could be crucial for your success. Now, let me show you the entire model building process again. You have your raw data, you do feature engineering, where you clean up your data, you rename, you recode, imputation, and so on and so forth. Now, after that, you do data partition. Sometimes you divide into 2, sometimes you divide into 3. If you are building a regression model, usually it's advisable to divide into 3. But if you're building a classification model, you can divide into 2 as the usual practice. But if you still want to go further, you can divide into 3. And then the first thing you set your hyperparameter tuning. You build your model. Is an iterative process. And then you continue to compare your results before and after the hyperparameter tuning. Now, let's see some examples of hyperparameters. Let me tell you that there are different hyperparameters. There are different hyperparameters for different models. We have learning rate in neural network, for instance. You have, you can choose your learning rate. And then in you can choose your learning rate, and then in decision trees or random forest, you can tune or choose the number of trees that you wish to have. And you know that gradient boosting, all these other boosts, gradient boosting, they are usually tree-like models. So the common hyperparameters there are the number of trees, the depth of the trees, and the complexity parameter, CP, which determines how many trees are built in the ensemble. Sometimes you specify one of these, sometimes you need to specify all, or maybe just 2, depends. Then in nearest neighbors, that one doesn't have trees. So you don't have to specify number of trees in nearest neighbors. You have to study the model before you know which hyperparameter to tune, except if you just want to do a random search. You just set it as tune equals a particular number. But then, if you need to be specific, you need to be specific with the specific, the appropriate parameter or hyperparameter to tune for each model. So in KNN, for instance, you can specify K, which specifies how or determines how many neighbors to consider when classifying a new data point. Now, in logistic regression or SVM, usually logistic regression does not need mostly any hyperparameter to be tuned. You just build it like that. But in SVM, you can specify the regularization parameter, but the type of logistic regression, especially the ridge logistic regression or the lasso logistic regression, you can specify the regularization parameter. But if you're dealing with the usual logistic regression, it doesn't need any hyperparameter. So there's also in neural network, the most you can specify the batch size, which determines the number of training samples used in one iteration of the model training. So all these are necessary to know if you must build a good model. Now, let's proceed. Why are hyperparameters important? Why are they important? Number one, to enhance model performance. If you see, someone says something, and I quote, we had a meeting yesterday, and one of the professors that presented, she said, machine learning is not for lazy modelers. Machine learning is not for lazy modelers. And that is why we should be conversant with the no free lunch theorem. You must continue to practice. You must continue to examine and compare and build different models, tune different parameters until you get the optimal model that you will deploy for your research or for your organization. So machine learning requires rigor. It requires you to really sit down, build several models, and train several models rather, and specify different hyperparameters and try different tricks. You tweak it. That's what we call tweaking the machine learning model. You try maybe before balancing, after balancing, and so on and so forth. And then you get the best model to deploy. So all these are necessary to be able to get the optimal model, because if you don't get the optimal model that will predict accurately, especially even in medical sciences where we are, you could be toiling with people's lives, could be causing a lot of havoc. Or even in financial systems, you could cause a lot of loss in terms of the finances of your organization. So you need to really be careful. You need to really sit down and build a good model for your data. Now, you must know that if you do so, you are enhancing your model performance, you're avoiding overfitting or even underfitting. you know, and especially when you are building tree-like models, like decision trees. These tree-like models are prone to overfitting. And so we need to really tune. Sometimes it is not optional, or most times it is not optional, especially for tree-like model, like decision trees, boosting, random forest, and so on. So you need to be aware of all this. Now, how do we choose hyperparameters? There are three major ways. You can use grid search. That's the expand.grid function in R. Grid search, it will systematically select your hyperparameter from the range you have specified, and it will find the best combinations. And then until it is satisfied, it will go from one object to the other until it gets the best, and it will search for you. It's a very powerful function. Then you can also do random search. Just specify, just give it a number randomly selecting combinations of hyperparameters from predefined ranges. Of course, you must have been familiar with the ranges, probably from previous works. Otherwise, your code will not run. Then there's something known as Bayesian optimization, which is a more sophisticated method that models the relationship between the hyperparameter and the model performance in order to select the best hyperparameters based on the model. We wrote a paper on this recently. When it's currently under review. When it's available, I will share. So that's a new area, a new one. People are already familiar with all these grid search, random search, but you can, maybe for your work, you can introduce Bayesian optimization for hyperparameter. That could be something new in your research work. We'll talk more about it. Maybe in one of our webinars, we'll talk about that alone. Now, hyperparameter tuning is very crucial, and it's very important for building effective machine learning models. And you can get familiar with them. And that's what we want to do today. And we're going to go into the practical sections very shortly. And we're going to see how it could maybe probably enhance our model performance. But before then, let's consider some examples of these hyperparameters a bit. In support vector machine, you see something like C and sigma. They control the trade-off between margin maximization of the hyperplane and error minimization and the kernel width, respectively. Of course, in decision trees or random forests, you see M-try, which is the number of variables randomly sampled as candidates at each split. I've said it in K, nearest neighbor. You see K, which is the number of neighbors to consider, and also batch size in neural networks, which controls the number of neurons in the hidden layer. And the K is the regularization parameter. Now there's FL, or use kernel and adjust in naive Bayes, which control the Laplace correction kernel, kernel density estimation, and bandwidth adjustment in naive Bayes, respectively. Then there is N eta, that's number of iterations in gradient boosting. So all these hyperparameters are necessary most times for you to specify, and they will allow you to systematically search through a range of plausible values for your model hyperparameters. And all this is just to enable you to set up or to build a good model, an optimal model. Now let's consider some practical tips here. If you are to choose, this is what I'm talking about. Just like the models we had before, you just need to specify this one line of code before building your model. Then inside your train, you say tune grid SVM equals, tune grid equals tune grid SVM that has been specified here. Then Caret will recognize it and work with what you have specified here. In random forest, you can do this. As you can see, this is the C I talked about, and this is the sigma that I talked about previously. Look, C and sigma, which controls the trade-off between margin marginalization of the hyperplane. Now, random forest is it uses mtry mainly. And A-base uses these three hyperparameters, but it's not all the time you can choose all. You can specify all. Some of them are chosen by default, even in Caret. But if you wish to adjust just one of them, or two of them, or three of them, go ahead. You are the master of the model. Feel free to build your own model. The most important thing is to get an optimal model. Now for logistic regression, I told you it doesn't require any extensive hyperparameter except when you are doing ridge logistic regression or lasso logistic regression, which requires penalization of some parameters. So you just have to set the lambda, the penalization parameter. You just have to set the range for it, such that it will search through all this, be able to get the best. Now, k-nearest neighbor, the same thing. You might wish to choose different neighbors. And you can choose, for instance, now this is from 1 to 21 by 2 steps, right? It depends on what you want to do. You can even compare different steps in your paper, and you continue to check the results, and then you suggest the optimal value for a particular data or for a particular problem. So there are so many research questions. There are so many things you can do here. LDA does not have any specific, no typical tuning grid. So it is just parameter free because it works with distance like KNN. So, but you need to be familiar so that you don't go and you don't disturb yourself choosing hyperparameters for LDA. So we can see that some models do not need hyperparameters, some need. So that's why we are taking this lecture, so that we can get familiar with all these intrinsics of model building. Now, neural network is one of the models that really need hyperparameter and decision tree as well. So you need to be familiar with the type of hyperparameters to choose. We talked about the batch size and the decay rate, the learning rate. You can specify as follows. We're going to go into the practice very soon. Now, for learning vector quantization, you can also specify the batch size and the learning rate as follows, and K. It has some characteristics of neural network as well. Then for bagging, you have this type of specification, the complexity parameter, because it's a tree-based algorithm. It's a tree-based algorithm. So you need to specify as such. Now, boosting also, you need to specify the number of iterations, like I said, and then you tell it the method, because there are so many types of boosting. There are about 6 or 7 types of boosting algorithms, like GBM, ADA boost, FG boost, and so on and so forth. So you need to specify your hyperparameters. Now, let's consider for decision tree. I'm going to demonstrate this for you in caret. And we're going to use the method rpath, and we're going to specify the complexity parameter, which prunes the tree by penalizing the complexity of the model. Now, this could also be a topic. We also wrote a paper on the tree pruning, decision tree pruning. That's also a hot topic. You know, because people don't build decision trees, they don't prune the trees. Even if you are in the farm, if you are familiar with the farmers, they prune their trees, they prune their flowers all the time. So why can't we prune our models as well? You don't just leave your model like that and you deploy. No, you have to do something. So we're going to work on these in the practical section. I'm going to show you. So what I'm going to do majorly in the practical section is this. We install caret if you don't have it before, and then we will use our malaria data set that we already have. We will split the data into training and testing using this, and then we'll define our model hyperparameter. We can decide to use all of these or only the CP hyperparameter will do in most cases. Then we'll train the model with cross-validation method. The other time we use repeated cross-validation, but this time we're just using cross-validation, right? And we will use caret as usual, using the function train, and the method is rpath. And train control is the control we have specified here. And we even try to balance the data in a goal, at a goal. Then we'll put the true grid we have specified. It's just as straightforward as that. Then we'll evaluate the model to see its performance so that we can get the decision tree, the confusion matrix, which will show us the sensitivity, specificity, accuracy, precision, F1 score, balanced accuracy, positive prediction value, and all that. So we are going to also try to visualize the tree to see how the tree is, how the tree behaves, how it branches using the package rpath.plot. And we're going to plot the decision tree. Now, if you have questions at this point, let me hear your questions. Otherwise, we'll dive into the practical. Okay, we'll keep the questions till after the practical. Now, the summary of the steps is as follows. Data preparation, split your data, set up your model, do cross-validation, evaluate your model, and visualize your tree. And we're going to do all this in caret. So let me quickly dive into the practical section before I take the questions. I'm going to dive into the practical section now. Let me just run the R code for the decision tree. I'm going to run it afresh. If you can see my tree, my slide, I'm going to reshare my slide, my code. Now, here we go. Hyperparameter tuning of decision trees using Caret. So if you have not loaded your packages, here are some necessary packages to load. Caret itself, rows for random oversampling, this DMWR also for oversampling, tidyverse, we're familiar with tidyverse, rpad for plotting the decision tree, and rpad for plotting the decision tree, and ROCR and PROCR for the metrics. Now, let's get a feel of the models in Caret. Like we said, look at the models in Caret. Look at, we have almost 240, but they are increasing. I think there are about 270 now. Is increasing. So you can choose any model that you want to work with here easily. But the one we are choosing is rpad for decision tree. For decision tree, look at it, rpad for decision tree, this one, number 185. That's the one we are choosing for decision tree in this particular demonstration. Now you load your malaria data, which we have in our GitHub repo. And then let's check the dimension of the data. 337 observations of patients, malaria, or people that are predisposed to malaria that came to the clinic. This data was collected at a clinic or hospital in Nigeria. And I've sent the documentation of the data set to you. It has been published in Data in Brief. So you will see all the descriptions of the data. Now, you see that the data is well processed already. So we do not need to fill in any missing values. We do not need to bother ourselves with missing value. You can see, if you look at the summary, you see that there are no missing values in the data set. You can see, but let me warn you, if you are not having a data like this, you have to do something. You have to spend majority of your time preparing your data and making it to be in good form, fill in the missing values, do feature engineering, recode, rename some data sets and all that. Some variables, rename some variables and all that. But then here, the data is ready for use. Fantastic data set. Now, let's look at the names of the variables in the data frame. We have age, we have whether the patient is having cold, headache, diarrhea, jaundice, proscription, the gender of the patient, rigor, bitter tongue. All these are symptoms. Calcular urine, hyperpyrexia, fever, fatigue, vomiting, anemia, and all that. But this is the target variable. You must be able to identify the target variable because here we are working with label data. This is a label data. This is supervised machine learning, which is really about input-output mapping. So this is the output that we want to map with all these symptoms. So the severe malaria is what we want to predict, and it is a categorical variable. So that makes our work a classification task. Okay. Now, you can decide to do feature plot with this plot, with this functions. Let's load the library caret to do our feature plot. Okay, so we can do our feature plot with this. Okay, so let's see what happens in the feature plot. I'm going to get back to the feature plot. Maybe I'm missing a comma somewhere, but I'm going to get to it and then rename you specify the levels of your response variable. When it is 0, it is not severe. When it is 1, it is severe malaria. So it's predicting whether patients will have severe or not severe malaria using those predictors, those symptoms. Now let's plot to see the nature of the response. You can see that the number of people that do not have severe malaria, they are much more than those who have severe malaria. And so this is an imbalanced data set. Okay. We can also see it better using the ggplot specified here that I've written here. Now you can see the imbalanced nature properly, not severe, severe. Now, we will do something about the balancing very soon, because if you don't do something about balancing the data, the algorithm may be biased, may produce biased results, may be prone to favor the majority class more than the minority class, which is a positive class that we are mostly interested in. Now, let's go further by partitioning our data. So we partition using the 75-25 divide, right? Using caret, just use this function, create data partition, and then you divide into 2. So we are dividing into train and test, training and testing sets. Now we want to ensure that our response variable is actually categorical. So that's what this is doing, both for the training and testing set. Now, here is the grid that I defined. Here's the grid, the tune grid that I specified. Feel free to specify your tune grid. This is the tune grid specified here. You can change it, you can adjust it to see whether the results are different. I use only CP here. Now, I've specified it. If you want to see the grid, you can check it here. Look at the grid, about 10, then look at it. So now let's set up our cross-validation. Now it's as simple as that. This is a very important step necessary action you must undertake. You must set up your train control for cross-validation because you need a more accurate model. Now, notice something here. I am putting sampling here. Current can take care of it at a goal. The sampling method is smooth here. If you want to use rows, random oversampling, you can use this second one. You want to use upsampling, which is oversampling. To oversample, create synthetic data from this existing one to upsample this one to the level of this, you can use up. If you want to downsample this particular one to the level of this minority class, you can use down. So there are these options in current. Current is great for machine learning. Now, I'm using this one. I'm using smooth synthetic minority oversampling technique. Synthetic minority oversampling technique, right? So rows, things like ADASYN, adaptive synthetic sampling and all that can also be done using rows. I wrote another code for ADASYN from the scratch. You can check it out later. I can give it to you later on if you follow us in this webinar. Now, look at the way I've set it up so that it can take care of the tuning, it can take care of the balancing at the same time. You can do without or with or without balancing. Here, no sampling, no balancing. And then you compare your results, or you do with or without hyperparameter tuning, and you compare your results. Now, there's nothing much to do again than to go ahead and build our model. Now let's set our seed as usual and build our model. Give your model a name. And this train function is there in current to help you train your model. So what is going on here is this is the response variable. You are making it a factor. Don't bother, don't mind how this one was spelled. That's how it was spelled in the data set itself. If you change it, it will not run. Now, this is a formula. This is what is used for the mapping, the formula, this tilde function, symbol rather, what is used for the formula. So if you put a dot here, it means take the other 17, all the 17 predictors, all the 17 variables in the data, take everything as predictors. But if you like, you can specify it here. You can decide to say age plus, maybe those are the ones you want to use, plus sex, plus Coca-Cola, urine, and all that. You can decide to do that. But then we are just putting a dot here, and then you put comma as usual, then specify the data you're using. Data equals train. You don't have to say data equals over or something because you have already specified the sampling here. If you want to do oversampling, you say the sampling equals up here, and you see how it behaves. Then method is rpat. If you are building a decision tree, rpat is good. If you are building a k nearest neighbor, method equals knn. If you are building a linear discriminant analysis, method equals LDA, and so on and so forth. If they are building logistic regression, you can use GLM, method equals GLM, and so on and so forth. Then you put a comma, then you say the tune grid you have specified before is what you will put here. Look, the tune grid. I told you before in the slide that this is something you set up before building your model. You specify it. Then you just, while building your model, you put it there. You set it up, you put it there. Then we are good to go. You start, you can see it ran. As a matter of fact, let me see the time it took to run. Let me use the TikTok package. Let me say here, library TikTok, that one. You want to see the time it takes your model to run, you can see it there. It will show you. Now, let me go to the model and specify TikTok. Okay, tick. You put tick there. You see that? Then talk. You see that? So let's run it. You see what it gave us? 2 seconds. It ran in 2 seconds. 2 seconds. Very fast. But if you are building more advanced models like gradient boosting, that one could take 3 minutes to run. And this is also something you should consider in model building. Even when reporting your results, you should be able to specify the time taken for each model to run. That's also something to report. So that if policymakers, maybe in the manufacturing industry, they want to use your model, they say, let's go for the model built by our researcher. They pick up your research paper or something and they see it. They say, oh, this model is faster. Maybe their own concern is about the model being fast enough. And then they can decide to go for the fastest model. That could be their own criteria for picking or selecting a model. So that's what the TikTok is for. Now, print your results, right? You can see the CP that was used among all the ones specified is this one, 0.01. Among the tune grid, the hyperparameter will specify here. Look at all the hyperparameters and the accuracies and the kappa. Kappa helps us to know what is the, how closely related the predicted is from the actual. Take a moment to study it. You can see it. You can see. Then we can print our results in a more elaborate form. And then we can evaluate the model using the test data that was specified, right? Now, we build a confusion matrix. Now, the confusion matrix is what will help us to see the result. Take a moment to study this confusion matrix. Look at it. So you can see that. So what do you deduce from here? You can see the algorithm predicted not severe, when in actual fact, it is not severe. 41 times. It predicted not severe, when in actual fact, it was severe. 18 times from the test data. And then the algorithm predicted severe here, when in actual fact, it was not severe. The algorithm predicted it predicts severe, when in actual fact it was severe. So this is true positive. This is true negative, right? And this is false positive, and this is false negative. So the items on the diagonal are the correct items, the correct prediction. And so this is where all these other metrics were calculated from. Accuracy, which is the total of this one plus this one, the diagonal over everything, divided by everything here. Okay. And you can see the kappa. Kappa is from -1 to 1. The closer to 1, the better. It shows that the model is performing well in terms of prediction. Now, you see the p-value of the cross-validation results, the sensitivity, the specificity. Sensitivity is the true positive rate, and the specificity is the true negative rate. And PPV, and notice that PPV and precision, they are the same. And sensitivity and recall are also the same. So another name for sensitivity is recall. Okay, you see the F1 score, which is the harmonic mean of sensitivity and of sensitivity and precision. You see it here, and prevalence rate, detection rate, and balance accuracy is useful at this time because the data is imbalanced. So balance accuracy is just sensitivity plus specificity divided by 2. And so this is a result for decision tree. If you're not satisfied with your accuracy or with your metrics, you can keep tweaking your hyperparameters or change the balancing method and see what works better. Now, this is just a very great way to demonstrate to you. Now, let's plot the confusion matrix. You can decide to plot the confusion matrix. This is the plot, the confusion matrix, so that you can visualize it better. It's also good to see in your papers. Now, you can do variable importance to know which symptoms are contributing more. So severity or non-severity of malaria among the patients selected. So fatigue is taking the lead here, followed by bitter tongue and diarrhea. You can see those are the most prominent features among those patients according to decision tree. Another model can see another thing. That's why you need to keep trying, compare all the models. Now let's go ahead and visualize the tree to also show us the to buttress the point of the the variables that are performing or that are more important in the tree. Now you can see the tree. Just use this rpath.plot to plot your final model, right? You can see the tree. If I zoom it, you'll see it clearly. So this is the root node, and these are the leaves. These are the leaves. These are the decisions. You know, as a matter of fact, I want volunteers to work on this paper so that we can really publish this. I want 2 or 3 volunteers. If you're interested, you can write your name in the chat box. Now, we can develop this into a more robust research paper. We won't be able to interpret all this right now, but in the paper, we will interpret everything and break everything down into pieces. Now, you can see how this is coming. this is an interesting result. And see the important, the more they are, that's how, I mean, the more they are closer to the root node, that's the more important they are. And then you can see all the branches. This is not like the usual dendrogram. This is a decision tree. Now, let's see whether we can glean another result from the ROC curve, right? The ROC curve is also very important for judging our model. The area under the curve of the ROC. Let's see, you can do that by setting your type in the prediction to probability, and then your prediction, you specify really what you want to predict. And then, because it's the plot of the positive prediction rate versus false prediction rate, and then yes, TPR versus FPR, right? So we'll calculate them and plot. That's just it. That's what the ROC does. Then we can put the value there. We can put the value there. You can see the value, 0.54. So this is not an optimal model yet. We have to do something more. We can do something more to tweak it further, to make it better, or we compare with another model. And that is why I'm putting this exercise here, that you are going to, maybe if we have more time, ladies and gentlemen, or you practice it on your own, depending on wherever you are watching or whenever you are watching this, you can decide to use this code. I'm going to drop the code in the description box. You can decide to use this run or to build another or to train another model. Just follow all the steps here, and then you'll be able to build your own model easily, right? And look, this is what I have here. And please feel free to practice, practice, and practice. Make sure you practice, and I wish you the best in your data science and machine learning sojourn. Thank you very much for your time, and we are open for questions now. Over to you, Professor Dennis, to moderate the questions.